So now let's go back and to the PowerPoint, which is here. Let's get it up there. So we've actually run this Python and a lot more. And here are the next commands in that Python. And these actually, remember that top plot had 3 x's in it. So this is how you get those x's. You define 3 vectors, 0.2, 0.2, 0.5, 0.5, and 0.75, 0.75. Then you call a routine we're going to actually discuss in more detail later on, called classify 0. That actually invokes the nearest neighbor algorithm. It has 4 arguments. The last argument is 3, which is the number of nearest neighbors to look at. Test vector is the vector you're trying to classify. Group is the set of existing points which have already been classified, and labels is the classification of that set of points in group. So those are the 4 arguments. And remember, 3 is the nearest neighbors. And you just run that algorithm for these 3 test vectors. You get an answer, and then here we actually plot the answer with scatter Matplotlib functions. And if we look at any one of those, this particular slide goes through in a little more detail on any one of those set of 3 points. And here we just did the last one, 0.75, 0.75, which a test vector is set to the vector we want to classify. Answer is the result of the k nearest neighbor algorithm. And the way that algorithm works, which we'll go through in detail, is very simple. It takes test vector and finds the Euclidean distance from test vector to all the points in the array group. Then it takes those Euclidean distances and sorts them. And it finds that the smallest distances, rather the 3 smallest distances in this case, and those are the 3 points it's going to use to do the classification. It looks at the labels of those 3 points and finds the label that occurs most often, and it returns that label that occurs most often as the classification of the point given in test vector. Say the code will be given later on. So before we do that code later on, let's just finish the Python, which was in this example. And this is actually a little more interesting case. We have 1,000 3-dimensional vectors in this file called dating test set 2.txt. If you go to Harrington's book, he will give some interpretation about some woman trying to classify her dates and see which dates had various properties. But it doesn't, that's of course sort of irrelevant, at least for the mathematics. The mathematics, all it cares about is there are 1,000 vectors. Each of those vectors has an x, y, and z component. They're vectors in 3-dimensional space, and they're all already classified by the woman who was classifying her dating partners. And now she wants to feed in a general 3-dimensional vector, which is a classification of a potential new date, and then she'll see whether the date falls into the undesirable, sort of desirable, or desirable classification. So here we now have actually 3 colors, red, blue, and green. The file is just labeled 1, 2, 3 for the classification. I say this here, the classification is given to you by Harrington in the book. So that's this Python here. Now we plot the middle graph of the set, which is the unnormalized results. And that's done by just defining a subplot. That's the figdating.add subplot command. Then we do a scatter of the x. And here we're only doing x and y, but ignoring z. These plots are 2-dimensional projections, ignoring the z component, the 3rd component. And Pete Harrington has designed this particular data set so you can actually see the division among the components just from the X and the Y components. And when you're doing this thing for real, you'd like to have each of the components having roughly the same scale. And that typically, the typical way of doing it there actually is to take every component, say here the component is X, Y, or Z, and you normalize it, say that mean of 0 and standard deviation of 1 in each coordinate direction. This particular code here does something which is probably, at least in this example, equally good, which is to make the minimum value 0 and the maximum value 1 in each coordinate. That might not be quite so good, that second choice, if there was a wide variation in the values. But for this case here, where the values don't vary over drastically, that's a perfectly reasonable thing to do. So at the end of this show command, we actually have outputted the plot with its 3 subplots, which is what we saw when we ran the Python. Here we reproduce that plot on this slide, and let's just discuss it quickly. So the top plot we've is this case of 4 points. These are the 4 circles, 2 red circles near the top right, 2 blue circles near the bottom left. And then we have 3 points in the middle. Those are the 0.2, 0.2, 0.5, 0.5, and 0.75, 0.75 test vectors. And then it's colored them according to the classification. The first 2 are colored blue, and the third one is colored red. And the only one where there's any possible, not trivial answer is the one in the middle, the 0.5, 0.5. If you just if you just look at the actual values of the circles, the input points, you will easily realize the 0.5, 0.5 will be classified as blue, because actually the red ones are slightly further away. Now the bottom 2 plots are essentially the same plot with minor scale changes as plotted, although the actual values of the axes are drastically different. On the graph at the bottom, the axes run from 0 to 1 in the X and Y directions. In the plot at the top, they run from 0 to 25 for Y. So this is the plot in the middle. They run from 0 to 25 for Y and 0 to 100,000 for X. That 100,000 is a big number because it's frequent flyer markers. So at this stage here, we're not doing any nearest neighbor classifications. We'll do that on the next discussion. All we've done is plot the 1,000 points with the classification that Harrington gives them. So there is no nearest neighbor algorithm applied.